Hello, I am Junbom Cha in Neighbor Global AI. I'll introduce our work, Fuchsia Compositional Font Generation with Dual Memory. Our goal is to generate a font library from Fuchsia reference samples. The number of glyphs in a font library is varying from scripts, but usually there are thousands or tens of thousands glyphs in a compositional script. Because of this glyph-rich property, compositional font generation task is very challenging and practically important. There are several previous studies for the fuchsia font generation. However, the existing methods mimic the global style well, but they cannot capture the detailed local styles. To solve this problem, we introduced the compositionality into the model, and it remarkably improves the stylization quality. The results are highlighted in the inset boxes. As shown in the figure, comparison methods generate completely different results from ground truth. Before diving into the method, let's look at the compositional scripts. In a compositional script, each letter consists of a combination of components. For example, every Korean letter can be decomposed into three components. This compositionality makes the script glyph rich, which causes extreme difficulty in manual font design. For example, Korean script has more than 10,000 letters as shown in the figure. So this task becomes very challenging and practically important. In this work, we applied our method to Korean and Thai only, but there are many other compositional scripts like Chinese, Hindi, Arabic, and so on. Then, why the previous method cannot capture the detailed local style? They choose the reference samples totally randomly, which means they assume the entire target style can be extracted from any random sample. However, local style is unpredictable from randomly selected reference. Our intuition is the local style are shared component wisely. So, if we can observe all the target components from the reference, the target local styles become predictable. From the intuitions, we propose two design principles. First, the model should be able to know the compositionality. And second, the model should see every component. Conceptually, we designed the encoder to decompose the input glyphs into the components, and the decoder to synthesize using the component-wise features. And we show all the components required to generate the target glyph. The dynamic memory handles encoded features component wisely and connects the encoder with the decoder. This is the whole architecture of dual memory augmented font generation network. In addition to the dynamic memory, we introduced another memory module, persistent memory. The dynamic memory handles local style features. The features are adaptively determined by input glyphs and encoder, and managed style wisely in the dynamic memory. In contrast, the persistent memory runs the intrinsic shape of components and global composition information. So it is shared between styles, and it is learned during training and fixed in the inference time. In the decoding stage, the features corresponding to the target components are retrieved from both memories and fed to the decoder. One last detail is the memory addresser, which is omitted in the figure. Most of memory augmented neural network estimate the memory addresses, but here we avoid the estimation loss by directly extracting memory address from the character Unicode. A character Unicode is decomposed into component Unicodes by simple law. We use the component Unicodes as memory addresses. We train the model on the generative adversarial network framework. Error loss, feature matching loss, and adversarial loss are widely used in GAN framework. Our feature matching loss is L1 distance between discriminator features of ground truths and generated images for every layer. And we use Hinge version of adversarial loss. These losses lead the model not only to generate real-life glyphs, but also to learn the compositionality. This is because our model does not use a content guide image, so it cannot generate plausible glyphs without compositionality. In addition, we adopt component classification laws for the explicit compositionality supervision. The encoded features from input and generated images are fed to the component classifier, and it is trained with the cross-entropy loss using the component labels. This objective enforces the encoder to decompose an input glyph to component-wise features, and the decoder to synthesize the decomposable glyphs. Finally, we use two multitask discriminator with shared backbone for each font and character labels. So our final objective is defined like this. We train the whole model jointly in the end-to-end manner. Okay, let's see the experimental results. This is the visual comparison on the unseen character set. In the last incel row, we highlight generation difference between models. The red box is ground truth, blue box is ours, and green box is one of the comparison methods. As shown in the figure, previous methods capture global styles well, but the detailed local styles are far from the ground truths. Only our method captures the local details well. In the quantitative evaluation, we evaluate the model more closely to the human perception, as well as the pixel level evaluation. Using the pre-trained style and content classifiers, we measure the two perceptual level scores, classification accuracy and mean FID. As shown in the table, DM font scores the best in the most of measures. Some methods show similar results in the content score, but our model dominates the stylization performance. To verify our model in the human level, we conduct the user study using Korean only find handwriting dataset. This dataset is also handwriting, and it is built in the wild without refinement. So its style is extremely diverse, including bad handwritings. The trends follow the perceptual level evaluation results. AegisNet and DM font are comparable in the contents evaluation, and our method is dominant in the style preference. To sum up, we evaluate the model with various datasets at the various level, and DM font dominates the stylization quality in all experiments. We further analyze why are the competitors devastated in the style scores, even though their results look similar to the ground truth at the first glance. The figure shows the result of nearest neighbor analysis. The red box indicates that the most similar with generated image is not from the ground truth styles, but from the training styles. Therefore, the previous methods almost memorize the training styles and they hardly capture the true styles of references. In the ablation study, we verify the effectiveness of our proposed dual memory modules. As shown in the table, each module improves the overall quality remarkably. And the last one, compositional generator, indicate the architectural improvements. The baseline networks consist of simple convolution and residual blocks. In the compositional generator, we introduce the global context awareness and local style preservation to help the model learn the compositionality by adapting self-attention block and hourglass block and low-level ski connection. To sum up, previous methods has memorization problem and failed to generalize to unseen styles. Proposed dual memory augmented font generation network overcome the problem by incorporating the compositionality into the model. As a result, DM font remarkably and consistently outperforms the existing fuchsia font generation methods. Thank you for your attention. Please refer to our paper and code for details.